All right. Uh, Good evening, everyone. Uh, so I guess we will start now, and probably this no one's going to join, I guess. Okay. So anyway, I will be uploading this video, and yeah, you can see it in YouTube. And if you have any doubts, you can contact me. Uh, this week, what we are going to do is we will quickly recap what we studied, especially the some part of force convection, some part of importance of viscous dissipation, and some parts of natural convection. Natural convection is not yet fully over. There are two more lectures yet in week 11. So we will discuss natural convection's problems in next week. This week we will continue our discussions on force convections. Okay, especially the viscous dissipation part. That is what we will be doing today. First, we will discuss what we studied in the lectures, and then we will quickly solve one problem. I have only one problem today, and it was also fairly straightforward. Uh, but I want to give you an idea how to solve this kinds of problem. Okay. Um, okay. Without further delay, we will get into. We will quickly recap. Let me check my recordings. Okay. So I guess we started, talking about internal force convection in the last week, and we analyzed, flow between the two parallel plates. Here, uh, when you have, you will be having initially you will be having a development of flow, and later the boundary layer starts developing, and at some point boundary layer merges and it becomes a fully developed flow, and our discussions are all fully focused on this region, fully developed flow. So we are not analyzing what happens before, we are not analyzing for the developing flow, we are only analyzing the fully developed flow. And uh, it is also, it's not just in terms of velocity it's fully developed, it's also in terms of thermally fully developed flow. And we studied sorry, we studied constant wall temperature and constant wall heat flux conditions. How the What are the few conditions that you will be, what are few simplifying approximations you can make when you have a fully developed flow, is what we did initially. And then based on overall energy balance, we were able to deduce the formula for heat transfer inside a uh, like forced convection heat transfer, right? So we did for a parallel plate, and we were able to develop the relations for Nusselt number using the integral method. And for this is for we did it for two different cases here. One is for as I said, constant wall temperature and constant heat flux. For constant heat flux we were able to fully deduce it, but in constant wall temperature, give me a minute, there is some problem. Okay. Okay. All right. So, sorry for the interruption. I was checking whether the audio is clear or. Okay. Yeah. So basically, what we did is we did it for two cases, as we discussed: constant heat flux and constant wall temperature. Constant heat flux, we were able to analytically derive it because of there was no non-linearity. We were not able. We no need to deal with it, and we were able to derive the Nusselt number uh, of flow inside a parallel plate, a fully developed flow, Nusselt number correlation. Uh, Actually, it's not correlation. We were able to, find it as a number, right? However, for constant wall temperature, because of this theta coming into the picture, we were not able to do it analytically. Instead, we did it, what do you call, using numerical methods. Um, and I hope you guys try to solve this using a shooting method. The methodology we already discussed in the class also, and also last week. Um, you can write a small MATLAB code to, uh, you know, uh, derive, to solve this, and you will end up having Nusselt number of 7.54. Okay, if you do this properly. That is what we did last week, and I think this week we also did circular pipe. I briefly discussed this last week, but if you have a circular pipe and let's say, then it becomes an axisymmetric problem. You have to solve the equations in cylindrical coordinates, and this will be your energy equation in cylindrical coordinate. And similarly, the constant heat flux, you will be able to solve it, but constant wall temperature, you need to use a iterative method. So for constant heat flux, in so here important part is we just solve the energy equation, because we the momentum equation we already solved, in fluid dynamics class, and you can use those relations here. Here, the momentum equation and energy equation is not coupled with each other, and that's why you directly solve the energy equation, and you will end up having the Nusselt number correlation for the constant heat flux, and you will also have, if you do a iterative process, you will end up having constant wall temperature Nusselt number relation. Okay, and then there is also something called Dieters-Bolter correlation, which is an important correlation for a turbulent flow in a circular pipe. This is what we usually use, but this is derived from the experimental analysis. Okay. Um, but main focus of this week's lecture was viscous dissipation. Um, for the internal force convection problems. When do you consider viscous dissipation? When is it important, right? Uh, so initially we discussed like how the viscous dissipation scales as, and it scales as u1 by h square. Now, if the h continues to decrease, then the u1 by h square will continue to increase, and since it increases, the viscous dissipation becomes important, right? And which means when you have a narrow gap, when you have very minute gap, then you will have uh, viscous dissipation term, and I mean you cannot neglect the viscous dissipation term. Till now we just removed it from our analysis. When you have a narrow gap, you cannot do it. That is what the scaling analysis gives. And then we did it for this simple quiet flow, for the this also like flow between a parallel plate, but it is a quiet flow because the upper plate moves with a velocity. In the flow between parallel plates, you will have pressure gradient which drives the flow. Here, the upper plate is driving the flow. We do not have any pressure gradient, so it's a purely shear driven flow, right? And for a purely shear driven flow, you can write the governing equation. This is a momentum equation, and you can solve, and you will end up having a velocity relation as a function of y, and again it's a fully developed flow, right? Then you can solve the energy equation for this, but now here we consider viscous dissipation because we are working on narrow gap, so we should have this viscous dissipation term, and this viscous dissipation term boils down to simply this for purely shear driven flow, and you keep substituting these, you take this relation, I mean you simplify this energy equation, and then you substitute the phi function appropriately. Phi is a viscous dissipation function, so you substitute them appropriately, and you will end up having a second order ordinary differential equation, and you will, if you solve it, you will end up having uh, the final uh, temperature profile. Now, this temperature profile, if you simply do not have a uh, viscous dissipation, then it becomes a simple linear profile, which will be a heat conduction problem. uh, but now, since you also have viscous dissipation, you will additionally you will have uh, an additional term which is going to contribute to the heating of your fluid. Okay. So now uh, we want to find out what is the heat flux, right? At the end of the day, we are interested in heat flux. So if you want to know the heat flux, it's nothing but minus k dt by dx at the wall. Here it is dt by dy because the wall is horizontal and you want temperature gradient perpendicular to it, so it's a dt by dy at the wall. So at the top plate, if you take the temperature profile, if you differentiate them, it will you will end up having this. And if you substitute in the heat flux at the top plate, then uh, you will end up having a heat flux relation, something like this. Now we are defining an important number here called Eckert number. This Eckert number is defined as u1 square by Cp into T1 minus T2. Okay. So if you think about it, this Eckert number is nothing but the ratio of kinetic energy to the uh, you know thermal energy stored, right? So Cp delta T is nothing but the thermal energy, and U square you can write it as U square by 2, right? It's something called kinetic energy of the fluid. So when you have Eckert number or Eckert number times if you have Eckert number to be very much greater than 1, then you need to consider uh, you know then your kinetic energy becomes more than thermal energy, so you no need to really have a viscous dissipation. But if the kinetic energy is uh, you know equivalent to the thermal energy, then you should include viscous dissipation. That is what this Eckert number roughly tells. Okay, it doesn't matter. It has nothing to do with whether internal energy is getting, or the thermal energy is getting converted to kinetic energy, or kinetic energy is converted to thermal energy. It has nothing to do with that. Although it is this ratio, it has just to say we have some part in the energy equation, some part of the energy equation deals with thermal energy, some part of the energy equation deals with kinetic energy. So now if the uh, thermal energy part is very high, sorry, if the kinetic energy part is very high, then uh, the thermal energy, considering thermal energy into that energy equation may not be important, right? So if you see a total energy equation, you'll be very clear. So let's say if we go back to energy, I think it's been long we studied energy equation. Yeah, here we studied energy equation, right? So now you have this is internal energy plus kinetic energy. So this is your total energy equation, right? Now uh, you can express this in terms of this internal energy equation, right? And also in terms of enthalpy. But anyway, this part is nothing but your you will have PDV and you will have viscous dissipation, right? So this is what this part is, right? Now you can use your Eckert number, okay, which is U square by Cp times T minus T, or delta T basically. Okay, this Cp delta T is your internal energy content, and U square is your U square by 2 is your kinetic energy content. So if your kinetic energy is not that much, then this part because of kinetic energy or because of velocity gradient is what this part is changing, affecting the internal energy. So if it is not that much, then you can safely ignore this part of the energy equation. Okay, that is why we define something called Eckert number. Right? And if you look at this heat flux equation that we derived, it has Eckert number, and you can add a Cp here, you can add Cp here, then it becomes Eckert number and the Prandtl number, right? So you will end up having heat flux to be simply uh, minus k delta T by H into 1 minus half of Eckert number times Prandtl number. So now here whether the heat flux is positive or negative, it will be determined by the Eckert number times Prandtl number. Okay, so if the Eckert number by Prandtl number is less than 2, then heat flux is negative. If it is greater than 2, heat flux is positive. If it is 0, then you no need to really worry about it. It will be uh, the heat flux will be 0. Yeah. So even though when there is a temperature gradient, uh, but because of Eckert number times Prandtl number is 0, I guess it is not 0. There is something wrong here. If this becomes 0, I don't think so it is 0. It is actually 2. Sorry about that. If this becomes 2, Eckert number times Prandtl number becomes 2, then uh, the heat transfer from the wall is 0. Okay, so there is no heat transfer even though when there is a temperature gradient. So there's some interesting phenomena happening here. Okay, so this is what we studied, and then we jumped into natural convection. In natural convection, we there is natural convection or free convection. So there is no driving force, externally applied driving force. That is how it is different from forced convection. In forced convection, we have velocity of the fluid moving, right? Because of pressure gradient, you have a velocity field developed, and also because of the top plate moving, you have a velocity field generated. Uh, so the velocity field which is generated has nothing to do with the uh, energy or thermal transport between the wall and the fluid, right? So the velocity is generated by other means. Now here there is no velocity is generated by other means. Instead, it is generated because of the temperature differences. Okay, so that is what makes the natural convection a little bit complicated than the forced convection. In forced convection, you can actually have a velocity profile initially, and after getting the velocity profile, you can substitute in the energy equation and you can solve them. Okay, safely. I mean, with some certain approximations, you can decouple momentum equation and the thermal energy equation. But here, the velocity itself is as a result of thermal energy equation. So we cannot really decouple these two. We have to solve it together. So that is the additional complexity you will have when you have a natural convection, because the velocity field is generated because of the temperature gradient. Okay, so this is the setup we have here. We have a vertical flat plate, and we are heating the flat plate, and since we are heating it, the gases which comes here takes away some heat, and when the gases gets heated, it becomes lighter. So since it becomes lighter because of the hydrodynamic pressure, it goes up, or hydrodynamic forces, it goes up. Since it goes up, it has to, if one parcel goes up, something has to replace that path or replace that position, then only continuity is satisfied. So that is what will set up this entire circulation. So it goes up, and it cannot go this side, so it has to go this side, and as it goes away, the it gets cools down. So then uh, because of gravity, it starts coming down, and in order to continue this process, in order to complete the loop, the continuity equation has to be satisfied, so it starts doing this circulation. And because of this, you will have a flow generation, and you will also have a temperature gradient, and the convection. This is how heat transfer is going to happen. Okay, so for this, we are going to use a 2D incompressible flow. Although density is changing, this is a special case. Still, you can use 2D incompressible flow. Uh, and the continuity equation and the momentum, y x and y momentum you have to do, and also energy equation. So all these equations you have to solve it together. Okay, so In our present analysis, we are going to restrict our analysis only for the vertical flat plate, heated vertical flat plate. But in general, if you want to, let's say, you know, analyze a natural convection process or natural plus forced convection process, right? Uh, you have to actually solve continuity x, y, and energy equation together. Okay, that's what all the CFD solvers does. For example, ANSYS or OpenFOAM or whatever the CFD solver that you take, they are going to solve this continuity, momentum, and energy equation together. Okay, there is a, of course, there's a big algorithm which goes inside, but this is what is happening. They will solve continuity, energy, momentum, and energy equation. So this is the literal equation that they will solve. Of course, they have to do some linearization. You have to apply some numerical methods and uh, discretization. They have to do all sorts of things that goes inside CFD. So they solve this entire PDE and they will be able to predict the velocity fields U, V, and T. Okay, but uh, we want to analyze it. We want to do some analytical approach. We want to take some analytical approach. We want to derive it on pen and paper. So that's why uh, we are taking a simplest problem here, which is a vertical flat plate, heated vertical flat plate, and inside of, let's say, in the boundary layer region, near the boundary layer region, how is my equations going to simplify, and if it simplifies, can I solve it and get some idea out of it? Okay, that is what we are doing here. So um, these are boundary layer approximations that we make. So please note that here x and y are switched. Till now you would have neglected y, but here you are neglecting x. Okay, because x is in this direction and y is in this direction. So flow is actually in the y direction. Okay, and that is why you are removing the equations in the x momentum. Okay, and in addition you will also have a gravity term. That is the one important difference. Till now, whatever the momentum equation that you would have solved till now for force convection, you did not have gravity, but here gravity is one main guy who's going to drive the flow, right? So that's why you have a gravity term, and then you have a energy equation. Again, we are here ignoring the viscous dissipation. Okay, here we are not having any viscous dissipation. Okay, and so the momentum and energy equation is coupled because the density is a function of temperature, and the temperature you will get only from energy equation. So you cannot solve these two separately. So you cannot find velocity vector or velocity field before solving the energy equation. It has to be dealt with together. Okay, so and then we make some, as I said, the boundary layer approximation that we are getting. We are studying only the boundary layer region, and we are going to use some fluid statics relation, which is dp infinity by dy. So how is the pressure going to vary along the y? That is simply going to be the hydrostatics. Based on hydrostatics, you can find that. So the pressure at one level is going to be the total weight of the liquid column above it. That is what this is. Okay, so dp infinity by dy, if you integrate it, it becomes p infinity is equal to rho gh, right? So rho g into h is the weight of the column above it. Okay, um, so this is one approximation that we are taking, and in addition is an important approximation called Boussinesq approximation. In Boussinesq approximation, we are going to say that this density is everywhere, like momentum equation, even in the convection term, and also in the gravity term, and also it is also in the pressure gradient term. But we are going to say that this density, we are not going to touch the density of these places. Only the body force, the density is taken to be temperature dependent, and this is a fairly good approximation, and we call it Boussinesq approximation. Okay, so and then we performed y momentum and then Taylor series expansion for the density. and because we want to write it in terms of volumetric expansion coefficient, and then did some non-dimensionalization for y momentum equation, and then we end up having something called uh, from the we define something called Grashof number, and Grashof number by Reynolds number is nothing but your Richardson number. So um, this actually tells that whether yours is a natural convection, forced convection, or mixed convection, right? So if the Grashof number is very much greater than Reynolds number, which means your buoyancy is dominant, and if buoyancy is dominant, natural convection is dominant. If it is very much less than Reynolds number square, then forced convection is dominant. So you can simply do a forced convection analysis. You don't need to do this natural convection analysis. If it is of the order of 1, which means those two are comparable, then it becomes a mixed convection. Okay. So these are the things that we studied this week. This will be coming in your week 11. Okay. I'm not going to go into this, but once week 11 lectures are posted, you please go through it, and we will discuss this more in next week. Okay. So before uh, we move on to problem solving, uh, we are not going to do this natural convection this week, although I discussed this a little bit. uh, if you have any questions regarding natural convection, we can you can come back and ask me next week, and we will be solving one of the question in natural convection. But this week we are going to stick with viscous dissipation. Okay. um, So this is the first problem that we have. I think Avinash Sivam has joined. Thanks for joining, Avinash. So what I will do is I will go forward and solve this problem. So this is the only problem I have for today, and it's related to viscous dissipation. So if you have any questions, feel free to stop me anytime. And also, for the people who are going to view this in YouTube, feel free to come back next week, or drop an email. Okay? All right. Um, so the question that we have here is, consider a hydrodynamically fully developed flow of a highly viscous oil. Okay, so this is as I said, it's a viscous dissipation. So it's going to be, you can take a viscous oil, uh, flow between a parallel plates, or in between two ball, in between the bearings, right? So the viscous oils viscosity is given, thermal conductivity is given, and it is, they are approximating it to be two horizontal parallel plates, flow between two horizontal parallel plates with the narrow gap. So which means viscous dissipation is important. Narrow gap of 1 centimeter, and uh, dp by dx is equal to 0, which means again it's a purely shear driven flow. And x being an actual coordinate, the bottom plate is stationary and the top plate is pulled towards positive x direction with a constant velocity of 10 meters per second. So it's a very much same like what we studied in the lectures. So you have a top plate and you have a bottom plate. It's a parallel plate, and the top plate is moving with u1, which is 10 meters per second. Okay, this is top plate, and yeah. So bottom plate is stationary. So this is not moving. Now, the top plate is subjected to a temperature of 200 degrees Celsius, and the bottom plate is subjected to a uniform temperature of 100 degrees Celsius. Okay. Now, okay, this is T naught, this is T1. Now assume the plates to be long enough so that the temperature profile is actually invariant. So which means temperature profile is not a function of x. For example, let's say this is x and this is y. Actually invariant means it is not a function of x. Okay. And now consider y equal to 0 at the bottom of the plate. So this is the plate, this is y equal to 0, and here y equal to h. Okay. All right. Now the viscous dissipation function is also given. This is the viscous dissipation function. We also derived it during the class. Now the first question is deduce the viscous dissipation function for the present problem. So which means I have to derive it for this present problem. It's a and find its magnitude. So you have to substitute all these values that we have for this problem. I think we partially did it in the lectures, so I am going to be a little bit quick here. So that will be your first question. The second we will come later. So you have phi to be 2 by 3. It will be time consuming. I'll just copy paste from here. Okay, for some reason my iPad is not working. Okay, maybe I will just try. So you have dou u by dou x minus dou v by dou y square. So dou u by dou x minus dou w by dou z square plus dou v by dou y minus dou w by dou z square. So this is 2 by 3. So let me write it down in 2 so that it will be clear. Dou u by dou y plus dou v by dou z square. Sorry, dou v by dou x plus dou u by dou z plus dou w by dou x plus dou v by dou z plus dou w by dou y square. Okay. Now we in order to simplify this, we have to know u and v. So for this case, this is we have a non-penetrating boundary conditions in both places. Both of these walls are strict, like uh, there's no there's a non-penetrating boundary condition implied at these two walls, which means whatever the fluid cannot pass through. So ideally the velocity here is 0 and velocity here also is 0, so there cannot be any other velocity form here. So ideally the velocity is 0 everywhere, right? So v is actually, I mean, the v component of the velocity is 0, so you do not have any of those terms. The w is, again, this is a 2D, so we do not have that too, so we can just remove those. So v's, w's and all will be 0. You will have only dou u by dou x or dou u by dou y. These are the two terms you will have. But here it's a fully developed fluid, they already said, so there is no actual invariance. So similarly, like you will also have u is not a function of x, right? So it can be only a function of y. So these are also gone, and yeah, there is no z, so this is also gone. So at the end you will end up having this phi function, viscous dissipation function, to be simply dou u by dou y square. Okay. Now we need to know the u profile in order to find the uh, velocity, in order to find the viscous dissipation function. So we can apply momentum equation here. There is no pressure gradient, so there is no uh, from the continuity equation we can remove the inertial term. So this is what we did in the class 2. We didn't go in detail, but it's already been done before. So yeah, basically it's a fully developed flow, there won't be any acceleration, so that's why this part is gone. and then you have pressure gradient, and then you have this, but the pressure gradient is non-existent, so you will end up having mu into d square u by dy square. Now is equal to 0, so it doesn't matter whether mu is present or not. So it's simply d square u by dy square is 0. So if you integrate it, you will end up having u to be c1y plus c2. So d square u by dy square is 0, means its second derivative of velocity is 0, which means the first derivative is going to be a constant. Then this becomes simply a linear, it's a straight line, right? It's an equation of straight line. So u will be c1y plus c2. Now you apply boundary condition, you will end up having at y equal to 0, u is 0, which is what the same case as this. At y equal to 0, u is 0. And hence at y equal to h, u is u1, which is the same for us. So you will end up having u to be u1 y by h, right? So if that is the case, so I'm skipping these things, u1 y by h, because this is already discussed in the class. Now you can find uh, so you can this, since u is a function of only y, you can write this as du by dy square, right? So if you find du by dy, it's going to be simply u1 by h. So this phi is nothing but u1 square by h square. So this is your viscous dissipation function. Now u1 square is given as 10 centimeters or 10 meters per second, and h is given as 1 centimeter, right? Isn't that the case? So h is 1 centimeter and u1 is 10 meters per second. In addition, there is also mu 0.1 Pascal second, and thermal conductivity is watt per meter Kelvin. Okay. Now u1 is 10 meters per second and h is 1 centimeter. You just simply need to substitute this to get the viscous dissipation function. So this becomes 10 square divided by 1 into 10 power minus 2 square. So this becomes 100 by 10 power minus 4. So this becomes simply 10 power 6. Okay. Now the question is, what you cannot simply write it because it's a viscous dissipation function. You need to know the uh, unit also. So what will be the unit? If you write it, it will be, so with this formula itself you can find it's a meters per second whole square divided by h is meter square. So it's simply 1 by second square. So this is nothing but 1 by second square, second power minus 2. Okay. So this is your viscous dissipation function. So then the magnitude is 10 power 6. Okay, for this problem. Now they're asking what is the second. So this is done. The second thing is, what is the temperature of the fluid at y equal to 1 mm. Okay, so the total h is 1 centimeter, which means that 1/10 of this position, what is the temperature? So it's going to be in between 100 and 200. Okay, so that is something we know, but what is exactly the temperature is what we are going to find out. And for this, what we need to do is, we already have the velocity profile. This is the velocity profile. So we have to substitute this in the energy equation. And once you substitute this in the energy equation, and you simplify it and you solve that energy equation, you will end up having temperature profile. And that is exactly what we did in the energy equation in the class itself. This is our full energy equation with the viscous dissipation term, and the viscous dissipation is like this, and there is no the acceleration term. So this term goes away, only the uh, heat flux term and the viscous dissipation will be together. And you solve them, you will once you solve it and apply the boundary conditions T0 and T1, you will end up having this temperature profile. So we will take from the class. So it's T minus T naught is equal to T1 minus T naught into Y by H plus mu into U1 square by. So in the interest of time, I'm not deriving this again because it's basically the same. Y by H minus Y square by H square. So we just need to, find a temperature at Y equal to 1 mm. So which will be equal to T naught plus T1 minus T naught into Y is 1 mm. So 10 power minus 3 by H plus mu into U1 square by 2K into 10 power minus 3 by H minus 10 power minus 3 square by H square. So it's just simple substitution of these values. You will end up having the answer. So T naught is 100. T1 minus T naught is 200 minus 100. So it's 100 into 10 power minus 3. H is, I guess it's 10 power minus 2, 1 centimeter. Plus this is 0.1 Pascal second, 10 square divided by 2 into 1. 10 power minus 3 by 10 power minus 2 minus 10 power minus 6 by 10 power minus 2 square is going to be 10 power minus 4. Okay. Now if you simplify this, what happens? 100 plus 10 power minus 2 is 10 plus. So if you do not have viscous dissipation, it's going to be simply these two. But we have viscous dissipation also. Okay. So now you have to simplify this. This becomes 10 by 2 is 5 times 10 power minus 1.1 minus 0.01, right? What happens? So it's 0.1 minus 0.01 is 0.09 into 5 is 0.45, and this becomes, am I missing something here? Oh, correct. Yeah. So this becomes 110 plus 0.45. So the temperature at Y equal to 1 mm is 110.45 degrees Celsius. So if there is, because of viscous dissipation, temperature is slightly higher. Okay. Ideally, it will be simply 110 degrees Celsius. So what I'm trying to say is it's a linear profile. Ideally, it will be a linear profile from 100 to 200, right? So from 100 to 200, it's going to be a linear profile, but because of viscous dissipation, its temperature is little bit large, so it's going to be something like this. Okay. So at 1 mm, this is 110.45 degrees Celsius. And now, yeah, if the dynamic viscosity of the fluid is increased, okay, how will it affect the viscous dissipation function? So viscous dissipation function is this. What happens when the dynamic viscosity of fluid is increased? That's the question. So ideally, if you look at this viscous dissipation function, you do not have any mu here. Okay. So in fact, in your energy equation, so it's mu times phi. Phi is a viscous dissipation function. The viscous dissipation function is purely a function of velocity gradient. Okay. Now, when you change the dynamic viscosity of the fluid, if the velocity gradient gets affected, then it will affect the viscous dissipation. It does not have a direct link. But in this present case, even our velocity profile doesn't depend on viscous, dynamic viscosity. So mu doesn't depend on dynamic viscosity. So hence, that the velocity gradient is going to remain same even if you change the viscous, even if you change the dynamic viscosity, and hence the viscous dissipation function will also remain same. It doesn't matter whether, it doesn't depend on dynamic viscosity, at least for this problem. Okay, so that is the third one. I guess you can understand this. So third is phi is not a function of dynamic viscosity. Okay, and the final question that we have today is, if the velocity of the pull of the top plate, so velocity of the top plate and the thermal conductivity of the fluid both are increased by the same factor. Okay, let's say I'm doubling them. Okay, doubling both velocity and thermal conductivity. How does the temperature within the fluid at any given location will change? Okay, so basically they are asking what is the dependence of temperature in terms of velocity and thermal conductivity. Okay, now um, we can address this from the equation T naught plus T1 minus T naught into y by h plus mu u1 square by 2k times y by h minus y by h square. Correct? 2k times y by, yeah. So if it's just the conduction, then it's going to be simply this term. But in terms of viscous dissipation, we have additionally this term. Now what they are telling, I am changing the thermal conductivity and also I'm changing u1. So ideally you are going to have some changes in this part of the equation. So let's say I define u1 dash to be some x times u1 and k dash to be some x times k. Now let's say you substitute them here. It's going to be remaining same for these two terms. For this term, it's going to be simply mu into x square u1 times 2 into x into k. So x, it becomes into y by h minus y square by h square. Okay. So the temperature is going to have this effect plus some x times mu into u1 by 2k into this part. So now if you increase, if you, let's say if x is you know positive quantity which you get multiplied, then which means your k has increased. So if k and u1 increases by the same factor, then what happens is the conduction part remains same, there is no effect, but the viscous dissipation part, there is some multiplication of this constant factor. So what happens is your temperature also increases, but the effect of increase may not be that much. At least for this case, it was just 0.45 degrees Celsius, right? There was not much of a, even if you try to measure it, it's going to be either 110 or 111, right? But strictly speaking, because of the viscous dissipation, when you increase K and U1, your uh, temperature increases. However, if you do not have viscous dissipation, whether you increase K or U doesn't matter, the temperature profile will remain same. Okay. So this is purely because of viscous dissipation. So ideally, in general, every flow will have viscous dissipation. In the narrow gap regions, the viscous dissipation's effect will be very high, so you cannot neglect from the analysis. But in general, whether it's a narrow gap or very large gap, doesn't matter, your viscous dissipation is going to be there. But this number that you have here, 0.045, is going to be 0.00005 or something like that. It's going to be very less and it's going to be very minute in terms of anything, in terms of our quantities of interest. That's why we usually neglect that. But in general, you will have this viscous dissipation. Okay. So yeah, so it's yeah, just the problem part of the flow in a parallel plate inside a narrow gap for viscous dissipation. This is what we will have here. And I hope this is clear. It's just straightforward implementation of formulas. If you have any conceptual understand, if you have any problems with the conceptual understanding of this uh, week's lecture, or this problem, uh, please let me know. I will be happy to answer your doubts. If not, we will conclude today's session, and we'll meet next week for natural convection. So I think I will probably go through natural convection again next week. This time we were on a little bit rush, and also it was not fully covered. So uh, there is also one more part that professor will be teaching in the next week lectures about order of magnitude and scaling analysis. So once that is taught, then we can discuss that together, and we will solve some problems on natural convection next week. Okay. Uh, and as far as your questions of week 10 is concerned, I guess it's all straightforward, conceptual questions. If you have gone through the lectures, you should be able to answer them. And yeah, so if you have any questions, please let me know. If not, thanks for joining. Thanks, Mustafa and Avinash Sigam, for joining.
Thank you, sir.
Yeah, welcome.
Sir, what about the rhenology of the fluid mean?
What about the
Rhenology of the fluid.
rheology of the fluid? Okay.
Rheology. Yeah, okay, I mean, I take checking rhenology or rheology.
Yeah, yeah, yeah. I think that is one of the question, right? So I will.
Ah,
Uh, so I may not be fully giving you the answer, but rheology, it has to do with I guess the viscosity,
hmm.
right? So are you aware of rheology? What is rheology?
No, sir, why this I'm asking?
Okay,
I have no idea about rheology.
right. I understand. So let me open that question.
Sir, also the eighth and ninth question, there is a technical issue with the mark is added incorrectly.
For uh, which one? The week
Eighth,
8 and 9.
eighth and ninth, one question. One is partial, one in partial, all of the above are
Right,
wrong in spelling. It same is I mailed it to you, and also from the review form also.
right. Don't worry about it.
Okay,
It
sir.
will be corrected soon. So they will take some time from the NPTEL to correct
Okay.
it.
Okay.
Uh, Hopefully wait for another 1 week. Okay,
Hmm.
uh, 1 week or 2 week.
Okay, sir. Okay, sir.
By week 11, if it's still not getting corrected, then I will ask what happened.
Okay.
Okay. So this one,
Actually, is the first question.
um, Richardson is independent of rheology of the fluid state purpose. Okay. So the Richardson number, the rheology means your viscosity basically. So uh, let me also explain it a little bit carefully.
In
Re
lecture, for 50 to 54 lecture is the this not mention this about this.
What? Right. So rheology is like flow and deformation of matter. So basically, it has to do with stress and strains. Mm, Usually, from the rheology studies, we try to find the viscosities. That is what my understanding is. That is what actually means. It whether it depends upon the flow of the fluid or not. And in this case, the flow is going to be determined by the viscosity. Okay, especially in the studies of rheology. So that is what they are asking, whether the Richardson number is dependent on the rheology of the fluid or flow and deformation of the fluid, whether it is dependent on that. So that is what you have to answer.
Whether it is independent of viscosity and deformation. This is asking
Exactly.
now.
Yeah. So that is what rheology means. The
Okay,
rheology is a
okay.
study of,
Deformation and
deformation and
viscosity.
in solids and
Viscosity.
fluids both. And
Oh, and also viscosity.
yeah, so deformation, what and all it depends on, right? So
Okay, okay.
it has to depend on viscosity. So
Okay,
which
okay,
means whether it depends on rheology or not, it has to depend on whatever the parameters the deformation of fluid depends on.
okay,
Okay,
sir.
so that is how you should answer this question.
Okay, sir.
Okay.
Actually, boys ने concept
Okay. So this one, sixth one, or
uh,
you have some other question?
6-1.
Okay. So the Bose-Einstein approximation in natural convection states that density is constant in the energy equation, while it varies with temperature in all terms of the momentum equation. Yeah. So uh, whether it is true or false, that you need to say, but we discussed this a little bit in the class, right? So Bose-Einstein approximation is uh, so this is what the Bose-Einstein approximation. You should consider density to be a function of temperature, but we are making this approximation. So in your momentum equation, you have density in the convective part, you have density in the this dp by dp infinity by dy becomes rho g based on fluid statics, right? So you have density here, you have density here. Now the Bose-Einstein approximation says that I'm going to consider density to be a function of temperature only in the body force term. Okay, so that is what the Bose-Einstein approximation. So whether the statement is true or false in the assignment, that you have to figure it by yourself, but you understand the Bose-Einstein approximation, right? So
Okay.
only in the body force term you are considering the density to be a function of temperature. If not,
Left side row is not concerning.
right. Otherwise, all other terms it's going to have rho to be simply rho infinity. So
Okay,
you
sir.
will end up having a y momentum equation, something like this. Okay.
Mm.
So this is rho g. This dou p by infinity is rho g, rho infinity g, because of Bose-Einstein approximation. So rho infinity minus rho is what you did here. Rho infinity minus rho into g, right? And this part is rho infinity, which is also stays as rho infinity. So only this rho is a function of temperature, and that is what is Bose-Einstein approximation is.
Yes,
Okay.
sir. Okay, sir. Okay, sir.
All right. Any other questions
Okay.
you have?
No, sir. No, sir.
Okay. Any questions Avinash Shivam has?
Sir, in last week, question number 4, sir. Pressure
Last
is a function of.
This
last
previously this discussed it.
Okay, okay, sir.
So
No
it's
problem. Now
week
this
9.
discussed it will be clear and just within 2 weeks. No problem. That is
Ah,
discussed.
oh,
Okay.
this one, fluid pressure. Yeah,
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 yeah.
yeah.
Same
Yeah,
is
I
the same is
guess.
Yeah.
discussed. 10 minutes before same is discussed it. No problem.
Okay, okay. Yeah.
Okay, okay, sir. Okay, sir.
So did you guys get any reply for the email that
No,
you
sir.
posted in the
No, sir.
forum?
No, 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 sir.
No, sir. No, sir.
No, right?
May,
So
only you only replied for this.
yeah, yeah, that is fine. In the forum, you didn't get any reply, right?
No reply, no
Yeah,
reply.
No,
you will
sir.
reply. You will get a reply soon. Don't worry about it.
Understood.
Okay.
Okay, sir.
So what about the actually here PhD scholars in
Okay.
NIT Puducherry?
Both you and Avinash. Oh,
Yeah.
nice,
Yes,
nice.
sir.
Actually for us, an NPTEL course is mandatory for our coursework.
Okay, okay, okay.
Okay, there were minimum mark is required. We are preparing for this. We are not only for certification course. This is our coursework also. One
Okay,
paper
okay.
had to compulsory to take NPTEL course.
Okay, 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 okay.
Okay, it is mandatory for all for it. So what will the examination pattern?
Hmm.
Actually, it will be some questions are coming for assignment also. Any
Uh,
weightage for?
so you may not end up having repetitive question from assignment. You will have a new questions in your end semester exam.
Hmm.
But the questions will be similar to what we are doing here, right? So we'll be solving, there will be some in conduction, let's say there will be some problems with numerical values that we already solved, right, in the previous lectures, and also in the assignment there will be some conduction with heat generation. In the convection, mostly you will deal with the conceptual questions like you saw in assignments. Uh,
Actually, I have taken a NPTEL course in my MTech course.
mhm.
There were 30-40%, up to 50% questions, same questions repeated from assignment.
Some courses are like that. Some courses are
Mm.
like that. I'm
Mm.
not sure about this course. So usually they do not repeat it. Uh,
Mm.
but you will also have new questions. So um, I cannot clearly say that whether if you just do assignment, it may not be enough.
Last week we can know how it is before examination. 1 week before,
Hmm.
can we know examination pattern?
Um, what pattern do you need? What kind of
Actually,
information you need?
also other students from NSC Puducherry were taken 8 week course. The assignment questions are repeated for also. I out of 50 questions, 30 questions are came from assignment, same question.
Okay. Then you better, then you
Mm.
better, go through assignment questions also one. But these questions are very easy. You no need to worry too much
Mm.
about it. Uh,
Actually, the questions are too tough, too conceptual question.
okay.
Actually.
So, uh, see, the concept. If you ask me, I would say the conceptual questions are, easier than the problem type questions.
Some questions are wrong answers are justification. We are go justification. That some answers are come right.
So,
Actually, in previous seventh assignment, I had cleared a doubt regarding dp by dt is a flow work, whether flow work or not. I
yeah,
had cleared doubt from in the online section.
yeah.
I have to ask you the explanation too. Actually, you have replied dp by dt not can be say flow work.
Mm-hmm.
I answered from this online section, but answer is wrong.
Oh, where is this? Which question
The
is
dp
it?
by dt is flower. In NPTEL assignment question, dp by dt is a flower. I answered based on our online section. I
Mm-hmm.
clarified the
Which
doubt.
one is it? Quiz 7 is
dp
it?
by dt. dp by dt is a flower.
Where is it?
dp by dt.
But which question is it?
A seventh assignment. Seventh assignment.
Seventh assignment. Mm,
Seventh or eighth, maybe eight, maybe eight.
okay. Let's see.
Eight.
Oh, okay.
B30.
Mm,
Based on I clarified from online section. I asked
mm-hmm.
with you whether this dp by dt is a represent flower. From
Mm-hmm.
online section, I clarified and answered.
Right. Okay, 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 okay. See.
But
Mm-hmm. Mm-hmm.
based on your comments, I answered, but the
Mm-hmm.
answer is wrong.
See.
Answer is both and B.
Okay. So, uh, see, you are right. So based on my comments, you said. Uh, but what did I say is the flow work is PDV, right? I'm going to repeat the same thing again. So the flow work is PDV, but
Okay. Again, I can
dp by
repeat.
dt, dp by
Again,
dt in itself contains the flow work. Here they didn't clearly say that flow work is equal to beta t dp by dt, right? So dp by dt is some form of representation of flow work. It's not exactly equal to flow work. So uh,
What will be the correct answer? Is it represent flow?
no, it should represent flow work. That's what I'm telling. So uh, pdv is the flow work. Okay, pdv is the flow work.
Yeah, that I know. But the
Okay,
DP by DT is
dp by dp by dt, if you expand it, what happens? There will be a flow pdv in it, right?
okay. Actually, some questions of this kind.
Okay, yeah, yeah, I understand that there will be
I'm not.
confusion.
I'm not telling your comment. Your comment is wrong. Maybe both answers are correct. Maybe somewhat extent both answers are correct now.
uh, yeah.
We are seeing with different angle both answers are correct.
Hmm.
This is the UG based questions now.
Right, right, right.
Okay, we are thinking basic level.
Yeah, probably. Maybe I'm also
Why
overthinking it.
sometimes
See, uh,
both have same argument.
yeah, these see, these are, these are, it has ambiguity in it. I understand that. Uh, See, you have this PDV, right? So this PDV, once you substitute it, you have this PDV, and this PDV, that PDV gets cancelled. So basically, you are end up having this entire thing. If you decompose it, you will end up having PDV work. So in this equation, what represents PDV work? If you ask me, this is what represents PDV work, or this is where PDV is coming in, right? Which means
Partially coming.
partially coming, exactly, yeah, partially coming. So which means the flow work is partially coming inside this term. So that's why they also use the term represent. um,
Mm.
but you are right, I mean, it can be ambiguous, and these are, it's a little bit
Mm.
difficult to understand.
It is one angle it will be say flower in one
Yeah,
angle it can be say.
yeah, I agree.
Both are correct.
Yeah,
Both have same kind of justification.
yeah. So you
Some questions
cannot
are
also
like
ask them that this is wrong, so that is also a problem.
if one is telling this is a flower, it is correct. This one is coming is not flower. Both are correct.
Right, but
Why is some questions are like coming like that like this in so many questions?
hmm, 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 hmm.
So
So
many questions like
yeah, but don't worry about these kinds of question much. Okay.
mm.
um
Actually, if you are fail on getting below C grade, we will try to repeat the same question.
I see. Okay, okay.
Actually, we are the first batch NPTEL mandatory. For our seniors, NPTEL is mandatory.
Mm-hmm.
Yes, sir. In new regulation, they have made
And
it
the other
mandatory, sir.
regulation
That's
NPTEL
why.
is mandatory.
Okay.
If it is simply a course, NPTEL certification course, not to worry. If it is fail, we can reappear. No problem.
Mm-hmm. Okay, but uh, not all the questions will be like this, so don't worry about it. There will be one or two questions like this.
Okay, sir.
Yeah, so don't worry much about it. So at the end of the day, you should have P and B in the flow. So
Whether it is coming as like a previous type assignment question, some questions are repeating end semester exam, some percentage.
yeah, maybe for this course at least you take this as a right answer. Although I would have told that dp by dt is not exactly flow work, but flow work is coming inside the dp dt. So uh, yeah, do not think much because it's a UG course. We are PhD students. We think too much. So that's fine.
Based on UG, it is not power. Based on PhD, not power.
No, that's not what I'm saying. See, this represents flow work. I still agree with whatever they are telling. Okay,
Uh,
this
uh,
represents flow work, but it's not exactly equal to flow work.
uh.
That is what I'm telling.
I
So
answered it is not a power. I don't got that. No problem.
yeah,
I scored ninth mark. Only one questions are wrong. This question.
okay. So then, if it repeats in the exam,
Uh,
please, correct it.
okay.
Okay.
Okay. If it is a came in examination, you have to write. It is a power. Okay.
Yeah.
Okay.
So
Okay. Fine.
usually, so don't worry much about it. These kinds of questions, they will not repeat that much. But
Okay.
but whatever they are telling is true. It's not like their answer is wrong. So dp by dt, it also represents flow work because it has pdv in it. So if you expand it, you will end up having pdv. So it also represents flow work. You cannot deny that it does not represent flow work. So they played with words a little bit. So usually these kinds of things you will see in MCQs. These kinds of things you will see in kind of competitive exams, right? So they play a little bit with words. So similar thing happened here. So don't worry much about it. Okay.
Okay, thank you.
All right. Any other questions?
No, sir.
Okay.
No, sir. No, sir. Thank you, sir.
Okay. Then we'll meet next week then. Thanks for joining.
Thank you, sir.
All right. Bye bye.